Hey everybody, it's Coach Stolmer again, coming to you with part two of the not nuclear chemistry, thermochemistry unit. Today we're going to finish talking about exothermic processes, and we'll introduce the specific heat equation and work on some calculations using that. And then we'll talk about something called colorimetry, which is not as complicated as that word might sound. All right, so let's just jump right into it. Got a lot to get through and don't want this to be too long. We introduced exothermic and endothermic processes. Last video, exothermic process, any sort of process that results in the overall loss of energy or energy is being released throughout the process. Endothermic processes are processes that require input of energy, or the overall energy of the system it increases throughout the process. We can graphically represent these two processes, and that's what we're looking at right here. This is the graphical representation of an exothermic process. If we look down here, it says reaction coordinate, and that might be a little confusing, but basically what we're saying is that the origin point is before the reaction has happened, and as we move this way down the x-axis, that's basically a timeline of the reaction. So the origin point, the reaction hasn't started yet. At the end, the reaction is complete. So this is basically a timeline of how the reaction is proceeding from beginning to the end of that reaction. The y-axis is really simple. It's just how much energy there's. Low energy down here, obviously, high energy up here. So for exothermic processes, these are processes that release energy, so we can expect to see our graph start high, because this is going to release energy as it goes through. So the energy of the reactants, the energy at the beginning of the process, is high. As we proceed through, we get this little bump here. This little bump is known as activation energy. Activation energy is it's kind of like the energy that you need to kickstart a reaction. Not very few reactions in this world are 100% spontaneous. Most of them require some sort of activation energy, some little bump of energy to get going. The way what I compare this to is a ball sitting on top of a hill. If the ball is sitting there with no energy acting on it, that ball is just going to sit there. But if some kid comes along, or a strong gust of wind comes and gives that ball just a little bit of tap, little kinetic energy, it starts rolling, and now once it starts rolling, the ball will roll down the hill on its own. It's that little bit of energy at the beginning that you got to hit it with, and then the reaction starts going. But after that little bump of activation energy, we notice the energy drops precipitously, and then we end with the energy of the products being lower than the energy of the reactants. And that's how we recognize an exothermic process. That energy starts high and ends low because energy is lost throughout this process. Here's a new term right here. The difference between these, the starting energy and the ending energy, is represented by this. It's delta H. H represents a term called enthalpy. We'll learn more about it later. But basically, enthalpy represents the change in energy of a system. Delta, that's just a mathematical symbol that means change. So this means change in energy, basically. Notice the value is negative. So we started high, we ended low, so the total change in energy will be a negative value. You lost energy. So anytime you see a negative delta H, or a negative change in energy, you know you're dealing with an exothermic process. So starting high, ending low, exothermic. So we know endothermic's the opposite, so what can we expect that graph to look like? Well, basically the opposite. Should start low and end high. Energy reactance is low. This time we're going to add energy. Notice the activation energy is a lot higher here because this is an endothermic process, so you're going to have to add a bunch of energy. You even add more than you end up with because it still needs that extra little bump at the beginning. So it actually will drop back down some, but overall, the total change in energy will be positive. The energy of the products is greater than the energy of the reactants. We finished with more energy than we started. And just like, this process is opposite of exothermic, the change in energy is opposite as well. A positive delta H, a positive change in energy means an endothermic process. This process has gained energy throughout. Exothermic energy of reactants is higher than energy products. Endothermic energy of reactants is lower than energy of products. Ultimately, whether your reaction or system is gaining or losing energy, we have to still abide by one of those altruistic rules that has come back over and over again, and that's the law of conservation of energy, mass, and matter. We've mentioned this law several times in terms of mass and matter, and now it's the same thing applies to energy. Energy cannot be created or destroyed, although if you look at some nuclear reactors or reactions, there's some perceived loss of energy there, but we won't worry about that. Law of conservation of energy says that energy cannot be gained or energy cannot be created or destroyed. Therefore, whatever's being lost by the system has to be being gained by their surroundings, or vice versa. Whatever total energy is being gained by the system has to be being lost by the surroundings. So that gives us this equation right here. The change in energy of a system, whether it's positive or negative, plus the change in energy of the surroundings, whether it's positive or negative, should always equal zero. Because that's telling us that whatever energy might be gained here would be the same amount of energy that's lost here. Or whatever energy is being lost by the system would be equal to the same amount of energy being gained by the surroundings. Ultimately, the change in the total amount of energy should be zero, because no energy is created or destroyed. So perceived loss of energy here really is being gained here. So let's say your reaction releases 9 joules of energy, 9 kilojoules of energy. This would be negative 9 kilojoules. Well, that 9 kilojoules would be gained somewhere, be being gained by the surroundings. So this would be positive 9 kilojoules. Negative 9 plus positive 9 is 0. Ultimately, in the end, change in total energy is always going to be 0. Okay? Alright, so that leads us into specific heat. But before we get to specific heat, I just mentioned a joule, and you're probably wondering what the crap a joule is. Well, here we go. This is what a joule is. It's a new unit for us, but essentially it's a unit of energy. It's a unit of measuring thermal energy. Now what it is exactly is kind of confusing. This is what it is. It's more of a physics unit than it is a chemistry unit. A joule can be broken down into newtons times meters. Okay, well, what's a newton? Well, newton is a kilogram times meters over second squared. So ultimately, 1 joule is kilograms times meters squared over second squared. Yeah. Could I actually put in all these numbers and make you work it out? I could, but we're not going to. We're just going to use joules. Joules, all you really need to know, is a unit of energy. It's not the only unit of energy we might come across. This one will seem a little bit more familiar. We'll also see the calorie. Normally you use joules, but every now and again you'll see problems that have the calories. Calorie is just another unit of thermal energy. There's your conversion factor there. 1 calorie is 4.18 joules. Now, this should sound familiar to you because you probably have heard the term calorie. You probably know food is measured in calories and whatnot. Well, this calorie is not the same calorie that you're reading on your nutritional information packets. That calorie is technically a kilocalorie. Why U.S. packaging doesn't use the term kilocalorie? Probably because it involves the metric system, and they don't want to confuse the poor American public about what a kilocalorie is. But so they won't. So the way they distinguish the food calorie from the actual calorie is on. If you look on your food calories, they'll actually capitalize the C. Yeah, that's how they distinguish. Instead of using the metric system, they use the same exact word but capitalize the C. So there you go. But that's neither here nor there. It doesn't really matter. 1 calorie is 4.18 joules. Alright, so let's talk about specific heat. What is specific heat? Alright, here's the textbook definition. It's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. There's your textbook definition. Now, what does that mean? Basically, it's how much energy it requires to change the temperature of whatever substance you're talking about. A substance, let's say a substance has a low specific heat. That means its temperature will change quickly once you start adding heat to it. It doesn't require a lot of energy to make its temperature change. So let's think about this. What might be a material that has a low specific heat? What kind of materials do their temperatures change relatively quickly once you start adding energy to them? Think about it. Hopefully some of y'all came up with metals. Metals tend to have pretty low specific heat. It doesn't take a lot of energy for a metal to get hot. And if any of y'all have any experience with cooking, you put a pan on the stove top and you turn the burner on underneath it, how long before that pan is hot enough to cook? Literally seconds. It doesn't take very long. So what would be one of the leading reasons for this? What can metals do that other it's not unique to them, but it's one of the things they're best at. That's right, they are good conductors. Good conductors typically have low specific heat. The better a conductor is, the faster that thermal energy can travel through it. Good conductors usually have low specific heat. Now, if you have a high specific heat, if your substance with a high specific heat, that means your temperature, it requires a lot more energy to be input before your temperature starts to change. So if good conductors typically have low specific heat, bad conductors typically have high specific heat. And one of the most common ones, and one you probably don't think about, is water. Water actually has one of the highest specific heats there is, and that is actually a really, really good thing for us. I forgot how slow this is. Why is water's high specific heat good for us? Well, let's think about it. This planet's surface is covered in about 3/4 of water, roughly, or 2/3. I can't remember what the actual number is, but it's mostly water, right? It's more than 50% covered in water. Why is this good for us? Well, where do we get our energy from? We get it from the sun, right? The sun is constantly bombarding us with energy. Even when it's on the night, we're on the dark side and it's nighttime, the other half of the planet is still getting blasted with thermal energy, radiation energy from the sun. So at all times, our planet is under bombardment of radiation energy. There's lots and lots of energy coming from the sun. So why is it good that our planet has so much water on it? It's because of that high specific heat. That water, with its high specific heat, actually it acts as kind of like a temperature control for our planet, because it can absorb a ton of energy without its temperature changing. So during the day, we get all this energy being input in that water, but that water's temperature doesn't really change, so it doesn't get overtly hot. And the same thing applies at night. When that water is now on the dark side and not getting that energy, its high specific heat means it holds on to that energy longer, and it takes longer for it to cool off. So during the night, it doesn't get super cold. If you think about places on this planet that don't have a lot of water, like deserts, you can see this really well, because the specific heat of dirt or sand is a lot lower than that of water, meaning it heats up a lot faster than water does. So in a desert during the day, when it's being bombarded by the sunlight, it gets really hot. And there's places on this planet where it can get, above 120 degrees. But what's really dangerous about the desert, other than not having water to drink, is that during the day, yeah, it's crazy hot. But at night, when you turn that heat off, because of the sand's low specific heat, it actually loses that energy really fast. So the temperature can drop to really low temperatures. And it's these big swing in temperatures that it's one of the reasons why being stuck in the desert is so dangerous, because during the day you have these extremely high temperatures, and then at night it can drop to really low. So it's really hard to deal with those kind of temperature swings. Now imagine if our entire planet was like that. We didn't have as much water. That would mean that during the day, on the light side of the planet, temperatures would be getting crazy high, and on the dark side of the planet, temperatures would be getting crazy low. So the fact that we have so much water on this planet is one of the reasons why life can exist. It acts as like a temperature control, because it can handle all this energy being absorbed, and then it doesn't lose all that energy when it's not being given to it. So water's high specific heat is one of the reasons why there's life on this planet to begin with. Alright. Okay, this is just a comparison of the two. You can see how big of a difference it is. Water specific heat, 4,184 joules per kilogram degrees Celsius. Sand, way lower, 664 joules per kilogram degrees Celsius. This absorbs and holds heat way better than this. Alright, so here's the specific heat equation. I'm going to go ahead and stop here, and on the next video we'll pick up here, and that way we can focus on the math. We'll talk about what these symbols are and what they mean, and we'll work through a couple problems. But for now, let's go ahead and stop here, and I will see you guys soon. Later.